Hello and welcome to this second and last tutorial in the mini-series on the statistics. And in fact, if you've been following along with this sort of course, as it were, this is the last tutorial in what in Scotland is called the National 5 curriculum, which is very similar to sort of O-level GCSE in other parts of the world, or the kind of maths that you would be seeing in high school in the age range, sort of 13 to 16, something like that. Now, I hope the series has been helpful and enjoyable at the same time. Now, statistics, I hope I haven't been too cynical in the first tutorial. I guess I wanted to just give you the sense that statistics can be used really in a very poor way to give you a convincing and yet very false sense of data. If used honestly and correctly, it can be tremendously powerful in condensing complex data sets and giving you very, very helpful insights and information. What proportion of statistics in the world, in politics and science and elsewhere, is used in that sort of responsible, honest way, I'm not going to comment, but it's not 100%. Right, in the first tutorial we were looking at a data set. It was 10 days in a row in some location measuring the number of hours of sunshine. And we used a method in which we identified the sort of middle value of that data set. That's called the median. And then we used what are called quartiles to get a sense of the variation around the median. In this tutorial, I'm going to use a very different method, which calculates something called the mean, and that's sort of the analog of the median. The mean is a way to try and estimate sort of an average value. And then we're going to calculate something called the standard deviation, and that's sort of the analog of the semi-interquartile range as a measure of variability. Let's see how we get on as we go though. So let me just repeat the data here. Just comparing back to my former notes, we have number of hours of sunshine on 10 successive days. So day 1 there were 5 hours of sunshine, day 2 6, very cloudy day, still fairly cloudy day, and then a lovely sunny spell, 6 hours, 7 hours, 8 hours of sunshine, but then a day again very, very cloudy, only 1 hour of sunshine, and then a sunny spell starting again, and then the data set stops. We don't know what happened on day 11. That's the data. Now when we calculate the median, the first thing we have to do with the data is order it. For this method though, you do not need to order the data. This is like a machine, this method. You just have an algorithm and you throw your data in and it spits out two numbers at you, the mean and the standard deviation. Now before we start these calculations, let me just introduce some notation. It's very common to label your data by a symbol with a number attached to it. The number really tells you which data point. So we're going to call the number of hours of sunshine x, and x1 is that number for day 1, x2 is that number for day 2, x3 is that number for day 3, and so on until we get x9, the number of hours of sunshine on day 9, and finally x10, the number of hours of sunshine on day 10. We're also going to introduce a symbol n as the number of data points. So n stands for the number of data points. In our case, that's 10. Okay. Now, when we calculate the mean, which when using this symbol x for the data points, we then call we denote the mean x bar. All right, so we pronounce that x bar for the mean. That is going to be the sum of our data. We're just going to add them all together, x1 plus x2 plus x3 all the way up to x10. divided by the number of points, 10. Let me just show you though how you can symbolically write that, because it's helpful to see this. Dividing by 10 is like multiplying by 1 over 10. So generally then for the mean you have 1 over the number of data points, and then this symbol is a way of writing that sum. We're summing over the values xi. We're taking that label I from 1 to the total number of data points. So in our case, I would be going from 1 to 10 of the data xi. That means x1 plus x2 up to x10. So this symbol has the name sigma. It's the capital sigma, capital S in the Greek alphabet, and just stands for sum actually. So when you see this this symbol sigma, it means sum whatever comes after this symbol, in this case xi, and it stands for that. So we can just do that. Let's add those numbers. Let's just do it on a calculator here carefully. We have 5 plus 6 plus 0 plus 2 plus 6 plus 7 plus 8 plus 1 plus 8 plus 7 equals 50. And then we divide that by the number of data points, 10, and happily we get an integer, which makes everything a lot easier, I can assure you. So the mean of the data is 5 hours of sunshine. And let's just compare that to the former tutorial when we were using the median method. We found the median was 6 hours. So that's actually quite interesting that these two different methods, the measure they have for, let's say in quotation marks, the average, or typical, again in quotation marks, sort of loose terms, but their measures are quite similar. So the median is 6, the mean is 5, so that's interesting. If different statistical methods give you similar values, you can have more confidence in the statistics giving you some true sense of the data. If different methods give you wildly different answers, then essentially you have a data set that is not amenable, at least to a kind of naive statistical analysis, and there may be reasons for that. It may be that it has extreme values in it. It may be something called bimodal, where it has sort of two different peaks in the data, as it were, two different kinds of averages, and you just have to have a much more detailed analysis to understand it. But here though, for our data, the fact that these two numbers came out similar is reassuring actually. Maybe our analysis can say something that's fairly meaningful. Now we have to calculate the variability through something called the standard deviation. Now I'm going to write the formula down for the standard deviation, which is going to scare you, not on purpose, but it probably will look horrendous. But then we'll see that the formula is just really a shorthand for an algorithm, and the algorithm is actually quite straightforward. So let me just write this formula down, and then we'll just move on. Something like just make sure I get this right. Yeah. Wow, so that's obviously just looks absolutely horrendous. But if we break it down, what it's saying is inside here, take the mean away from each daily value, square it, add all those squares together, and then divide by 1 less than the total number of points, and then take the square root. Well, we can do that, can't we? So let me do it this way. Let me have my data points written out. So 5, 6, 0, 2, 6, 7, 8, 1, 8, 7. I encourage you not to just kind of throw everything into that formula and hope for the best. I think it's best to do it step by step, because really this is a shorthand of an algorithm rather than just a kind of a monstrous machine. Let's first of all take each data point, subtract the mean and square it. And we'll just do it by hand because it's sort of interesting. Day 1, there were 5 hours of sunshine, which is actually exactly equal to the mean. When we subtract the mean from that daily value, we get 0, and 0 squared is 0. Day 2, there were 6 hours, which is close to the mean. 6 take away the mean is 1, and 1 squared is 1. Day 3, no sunshine. 0 take away 5 is negative 5, squared is 25. And already you start to get an insight into this standard deviation here, because you see those first 2 days were very, very close to kind of, in quotation marks, average weather according to the mean. And so the contribution that those data points have to the measure of variation is tiny, whereas day 3 was sort of an outlier. There was no sun that day. Its contribution to the measure of variation is going to be very, very large. So that's sort of interesting. Let's keep going. Day 4, there were 2 hours. 2 take away 5 is negative 3. All squared is 9. Next day there was 6. 6 take away 5 is 1. 1 squared is 1. Next day there was 7. 7 take away 5 is 2. Squared is 4. Next day there were 8 hours. 8 take away 5 is 3. Squared is 9. Let's pause here. This is interesting. Compare day 4 and day 7 here. This was quite a cloudy day. This was a very sunny day. Do you see how they each contribute the same amount to the measure of variation, though? Although opposite, they were equally different to the mean, and they will contribute equally to the measure of variation. Next day there was 1 hour, so 1 take away 5 is negative 4, squared is 16. Next day 8 again, 8 minus 5 is 3, 3 squared is 9. Final day, day 10, 7, take away 5 is 2, 2 squared is 4. So that is big step done in the algorithm. We've taken each daily value from the mean and squared it, okay? I don't want to be boring here, but this might be useful. Do you see how when I came again to the value 8 or I came again to the value 7, how I didn't just copy the number in, even though I'd done it before? I just worked it out again quickly. The reason for that is just a very quick little way of checking, because had I gotten a different value, immediately I'd have known there might be something suspect with the values I'd done before. If you just copy values down from before, but those values have an error, all you're doing is copying an error. So when you're doing maths, particularly things like this, where you have a bit of repetition, don't always just copy, just actually work it out again, because that's a really good, clever way to just do a check. That's what computer programs have built into them, that kind of independent checking to minimize the effect of bugs and so on. Don't let your errors propagate unconsciously. We now have to add this all up. So we want to sum this set of squares, okay? Let me use the calculator to do this. I'm going to try and do this really carefully because my calculator is old and not very trustworthy. So I have 0 gives 0. I have 1 plus 25 plus 9 plus 1 plus 4 plus 9 plus 16 plus 9 plus 4 equals 78. So that apparently is the sum of those values. I'm actually going to just do it by mental arithmetic because I really don't trust that calculator. 26, 36, 40, 49, 59, 63, 49, 65, 74, 78. Good. Okay. The algorithm now says divide that by 1 less than the number of data points. So to divide this by n minus 1. So that's going to be 78 divided by 10 minus 1 is 9. So we have 78 divided by 9 gives us 8.6 recurring. Okay. You can put a dot above a decimal place to indicate recurring if you like. Roughly this is 8.67. You might want to write it like that, just to 2 decimal places. But then we just need to take the square root. So the standard deviation is the square root of all of that as above, and that's going to give us, interesting, okay, 2.94. I'm going to just write that to 1 decimal place. So it's 2.9 hours. Right, okay, turn the calculator off. That's interesting. Let's compare, actually, to our first tutorial. Do you see how we got 6 hours for the median and our semi-interquartile range was 2.5 hours? Kind of a measure of variability. Here, we have 5 hours for the mean and a standard deviation of 2.9 hours. Pretty interesting. So quite similar. And that's maybe a nice note actually to end on with this little series on statistics, that these two methods, although completely different in spirit, have given us fairly similar kind of information about this data set. I hope this was fairly clear. Remember, with the method with the median and quartiles, there's a bit of dithering whether you have an odd or even number of data points and how you define quartiles. It's a bit kind of it's a bit confusing, exact definitions of quartiles and median, and I gave you the definitions that the Scottish Exam Board uses. I think what's nice about this method is that it is much more ambivalent about your data. It doesn't care about how many points you have. You literally use this formula here for the mean and this formula here for the standard deviation, and whether you have 5 points or 5 million points, it's very, very straightforward just to process the data and get out your answers. Good. Okay, so that, I think, is enough from me. I've given quite a lot of opinions in these 2 tutorials on statistics. Please take those with a very large measure of salt. But what I do hope I've gotten across is how to implement these 2 methods with some degree of care and some degree of sort of common sense. Common sense is a tremendous thing to have as an ally when you are dealing with statistics. And with that, thank you if you have been a faithful viewer through this quite long series. I think it's something like, I think it might be 47 different videos, something like that. So well done if you have actually come through the whole thing. If you've just been coming occasionally for various tutorials and you found them helpful, that's wonderful too. If you've enjoyed maths, you might want to continue with maths to the next level in whatever high school curriculum you have in your part of the world. I'm a physicist, but I use maths for my job as a theoretical physicist, and I really love this stuff. I just think it's so powerful. So I encourage anyone who enjoys this to just keep pursuing it, because whether you use it for a profession or just for your own enjoyment, it will really enrich the way that you appreciate the universe around you. So with that, thank you so much. Feedback is very much appreciated, and I wish you well. Goodbye.